Today we're going to continue our work with derivatives and take a look at something called the chain rule. But to set up the chain rule, I first want to look at an example of a problem that we have solved several times before. A problem like y equals 3x plus 4 squared. Now, in order to take the derivative, we've done it several ways. First way we did it was we did it as a polynomial. And we said, well, we can square this and say y is equal to 9x squared plus 24x plus 16. And then we can take the derivative of the thing like a polynomial. Y prime is equal to 18x plus 24. And then we took a look at it with a different view and said, well, let's solve it as a product, because we have a product rule. And the product rule says, we'll think about it as y equals 3x plus 4 times 3x plus 4. And now that it's a product, y prime is equal to the derivative of the first times the second plus the derivative of the second times the first. So the derivative of the first part is 3x times 3x plus 4 plus the derivative of the second is 3x times 3x plus 4. And then it's just a little bit of algebra to distribute. Give us 9x squared plus 12x plus 9x squared plus 12x. Combine like terms. 9 and 9 is 18x squared plus 12 and 12 is 24x. So y prime, our derivative, is there. A third way, though, to solve this problem that we're going to really look at today is to look at this problem not as a polynomial, not as a product, but the way it is given to us. The way it is given to us is as a composition, which means there's a function inside of a function. If you look at this function, we see the 3x plus 4, which I didn't want to delete. There it goes. We see this 3x plus 4 is squared. We've got some stuff that is squared, and it's really easy to take a derivative of something squared. It's 2 times something. Well, if we think about that as the guts of the problem, y equals some guts squared, that might be easier to take the derivative of. So the function is what I'm thinking about as the guts of the problem. So let's take a look at defining this clearly before we get too far ahead of ourselves. Defining this thing called the chain rule. Officially, the chain rule says that if y is equal to some function with a function inside it, then the derivative y prime is the derivative of the outside times the guts. The derivative of the outside with the guts times the derivative of the guts. Maybe I can make it a little more simple. Let's say instead y is equal to a function that has guts in it. Then y prime, the derivative, we take the derivative of the outside, treating the guts just like a variable, and then we multiply by the derivative of the guts. Let's take a look at that example we've been working with. We've been working with this y equals 3x plus 4 squared. But this time I'm going to think about the 3x plus 4 as the guts of the problem. Treat that as a single entity. And so if we were just taking the derivative of something squared, we'd pull the exponent out front and say it would be 2 times the guts, 2 times 3x plus 4. And then in order to justify this, we have to take the derivative of the guts. The derivative of the inside. The derivative of 3x plus 4 is 3. And so we have y prime equals, let's multiply 2 times 3 first to get 6 times 3x plus 4. And so finally, the derivative of everything is 18x plus 24. So rather than solving this as a polynomial by first multiplying it out, or as a product by writing the squared as a product, we can just take the derivative of the problem as it was given to us. We take the derivative of the outside times the derivative of the guts. And this makes it really easy to take the derivative of something such as 3x squared plus 4x minus 7 to the 8th power. If I wanted to do this as a product, we would have 8 products. That would be ugly. If I were to do this as a polynomial, we would have to multiply this out 8 times. It would be ugly. Instead, we'll do it treating the inside as the guts. We've got stuff to the 8th power. Well, we know we take the 8 out front, and we have 3x squared plus 4x minus 7. And we raise that to the 1 less power, the 7th power. And we can justify that move if we now multiply by the derivative of the guts. The derivative of 3x squared plus 4x we know is 6x plus 4. And that fast, we have calculated the derivative. We take the derivative of the outside times the derivative of the inside. Now, where the algebra starts to get really fun is when we combine the chain rule with the other rules we've seen, such as the product or quotient rules. And here's where the algebra starts to give us a ride for our money. Let's say y equals 2x times 5x minus 3 squared. Yeah, let's make it more interesting. Let's do 5x minus 3. Yeah, let's keep it squared. We'll keep this one simple. We'll get interesting in the next problem. Now, what you'll notice here is what we're really working with is a product. We've got 2x times the 5x minus 3 squared. But that second factor, the 5x minus 3 squared, has some guts in it. It's stuff squared. So we're going to use the product rule just like we did before to find dy dx. But along the way, we're going to have to use the chain rule to take the derivative of the second part. Now, the product rule we should remember is the derivative of the first times the second plus the derivative of the second times the first. So the derivative of 2x is just 2 times the second, 5x minus 3 squared, plus the derivative of the second. Here's where we're going to have to use the chain rule. We've got guts squared. Pull the 2 out front and subtract 1 from the exponent. 2 times 5x minus 1. And that's okay as long as we multiply by the derivative of the guts. The derivative of 5x minus 3 is 5. Because the highest exponent here is squared, it's just a bunch of squaring and distributing, we can do that. So let's go ahead and clean this up. First, we'll square. So we have 2 times 25x squared minus 30x plus 9 plus, let's multiply the whole numbers together. 2 times 5 is 10 times 5x minus 1. Then just distributing through parentheses here, we've got 50x squared minus 60x plus 18 plus, distribute the 10 through, we get 50x minus 10. Combine like terms, we've got 50x squared minus 60 plus 50 is minus 10x. And 18 minus 10 is plus 8. And we've got the derivative by using both the product rule and the chain rule in the same problem. Let's try another example. How about we do one that's going to involve the quotient rule and the chain rule. Let's say f of x is equal to the square root of 2x plus 1 over x squared plus 3x. Now remember, square root, whenever you see that, you should be thinking 1/2 power. 2x plus 1 over x squared plus 3x to the 1/2 power, because that's going to be easier to take the derivative of. And again, you'll notice here, we've got some guts to a 1/2 power. But what you might notice is inside those guts, we've got a quotient rule. We've got a top divided by a bottom. Part of mastering calculus is recognizing the patterns. What is the shape of this problem? So if we want f prime of x, if we want the derivative, we take the derivative of the outside, which puts the 1/2 in front, times 2x plus 1 over x squared, eraser, x squared, plus 3x to the negative 1/2 power. And then we multiply by the derivative of the guts. Well, the guts is a quotient. So we're going to use the quotient rule. Low d high minus high d low, square the bottom, and away we go. So low is x squared plus 3x. D high, the derivative of the top is 2, minus high, 2x plus 1. D low, the derivative of the bottom is x squared plus 3x. All over, square the bottom, x squared plus 3x squared, and away we go. We're not going to simplify this all the way, but there are a few things we can clean up. One thing we can clean up is the negative exponent. It's going to flip that over. So, as we flip it over, it's going to make it one big fraction. Now let's keep it as separate fractions for now. We'll make it a single fraction later. So we've got 1/2 times, and as we flip it over, I'm going to put the 1/2 on top and bottom. 2x plus 1 to the, flip it over, x squared plus 3x to the 1/2 power over 2x plus 1 to the 1/2 power. Flipping it over. Times this next fraction, let's go ahead and distribute. So we have 2x squared plus 6x minus, as we FOIL, we're not going to lose the minus sign. Someone's going to do that on the test. Don't let it be you. Don't lose the minus sign. 2x squared, we got to take the minus all the way through, minus 6x, I'm sorry, 2x cubed minus 6x squared plus x squared, minus x squared. See, I just did it. Don't let it be you. Two x cubed minus 6x squared minus x squared minus 3x all over x squared plus 3x squared. A little more algebra to keep cleaning it up. We're multiplying fractions, so I'm going to make this all one big fraction. So we've got x squared plus 3x to the 1/2 power times, combining like terms. Let's see, we've got a negative 2x cubed, positive 2x squared, negative 6x, negative x squared. It's going to be negative 5x squared. And then 6x minus 3x is negative 3x. All over a 2. A 2x plus 1 to the 1/2. And an x squared plus 3x squared. One last thing I want to do to simplify. I notice we've got a similar factor here in x squared plus 3x in both top and bottom. We can simplify that by subtracting the exponents, and since there's more in the denominator, the leftovers will be in the denominator. So in the denominator, we'll have 2 times 2x plus 1 to the 1/2 times x squared plus 3x to the 2 minus 1/2. Well, that's 4 minus 1 is 3/2. And so our numerator is left negative 2x cubed minus 5x squared minus 3x. That was a beautiful problem. I want to notice, though, in this problem, the long drudging out was really the algebra, not the calculus. The chain rule was pretty simple. The setup wasn't too bad. In the setup, we just took the derivative of the outside, pull the 1/2 out front, times the guts to the negative 1/2, and then the derivative of the inside, which we've done before, that's just a quotient rule. The algebra, then, was the simplifying, the FOIL, the exponent properties, the distributing, the combining like terms. Yes, there's a lot, but it's manageable. It's not that bad. It does take some time to crank it out, but you can do this stuff. It's not as scary as a big piece of paper makes it look. Let's do one that gets really ugly, but is very, very manageable. You can do problems now like g of x equals 2x minus 1 squared times x plus 3 all over the square root of x squared minus 1. This is probably a little more difficult than anything I could possibly put on a test because there's a lot of pieces here. But I want you to be able to look at this and see the pieces. You should see there's the piece of a quotient, a numerator divided by a denominator. You should see, as we look closer at that numerator, there's a product. 2x minus 1 times x plus 3. You should see inside that product there's also some guts. Similarly, in the denominator, you should see some guts. So this problem is going to use the chain rule twice, the quotient rule, the product rule, but you know how to do all of those steps. We just have to crank out all of those steps. So g prime of x is equal to big picture down to small detail. Big picture is a quotient. Low d high minus high d low, square the bottom, and away we go. The low is the square root of x squared minus 1 times the derivative of the top. Well, the top is a product. The product is the derivative of the first times the second plus the derivative of the second times the first. So the derivative of the first, well, here's where we see the guts. We take 2 times 2x minus 1, and then we multiply by the derivative of the inside, the 2, plus, oops, not yet, that's the derivative of the first times the second, x plus 3, plus the derivative of the second, which is 1, times the first, 2x minus 1 squared. So in the square brackets, we have the derivative of the product. Overall, so far, we've got low d high minus high which is 2x minus 1 squared times x plus 3, d low. And we should recognize that square root, we don't really do square roots, we do 1/2 powers. So times the derivative of 1/2 x squared minus 1 to the negative 1/2 times the derivative of the guts. The derivative of x squared minus 1 is 2x. Low d high minus high d low, square the bottom. So here we go. We're going to square the bottom. What happens when we square a square root? When we square a square root, the square root is gone. We're just left with x squared minus 1. And this one's not going to simplify as nicely. We could do the work to simplify it, but I'm just going to be content stopping here. We should be able to see that we did the quotient rule. It was low d high minus high d low, square the bottom, and away we go. All we did there was the quotient rule. Along the way, when we did the derivative of the top, we had to use the product rule. The derivative of the first times the second, plus the derivative of the second times the first. As we did that, we had to use the chain rule, because we took the derivative of the outside times the derivative of the guts. Similarly, we had to use the chain rule in the denominator because we took the derivative of the outside times the guts. So just because it looks ugly, it's just a longer process of the easy stuff we've seen before. Work it out and crank it out one step at a time. With all these tools, you might notice that sometimes we have multiple ways now to solve some problems. For example, if I wanted to solve 2 over 3x plus 1 to the 4th power, that's a great problem, and a lot of people try and solve it using the quotient rule, because they see it as a quotient, 2 divided by the 3x plus 1 to the 4th. And so we start setting up the quotient rule with low 3x plus 1 to the 4th, d high, well, the derivative of the 2 is 0, minus high 2 times the derivative of the bottom, d low, which, notice that's stuff to the 4th power. So we have 4 times the stuff now to the 3rd power. We just have to multiply by the derivative of the inside, which is 3. Low d high minus high d low all over square the bottom. 3x plus 1 to the 4th power. And there's nothing wrong with this method. We've just created a lot of algebra we need to do to solve it. One nice thing is 0 times anything is 0. And so we've got negative 2 times 4 is negative 8 times 3 is negative 24 times 3x plus 1 to the 3rd power all over 3x plus 1. Ooh, I didn't square the bottom. Square the bottom and away we go. Square the bottom. Whew. Get that on there. Low d high minus high d low, square the bottom. And away we go. So we've got 3x plus 1 to the 4 times 2 is 8 power. And now, since those factors match, we can subtract the exponents there, more of them being on the bottom. 8 minus 3 is 5. And that's right, and it got us the answer. No problem. But what if we had seen this problem another way? What if we rewrite the problem? The problem was 2 over 3x plus 1 to the 4th power. And what if you had noticed that, gee, that stuff to the 4th power in the denominator, we can pull it to the top if we make the exponent negative. You have 2 times 3x plus 1 to the negative 4th power. And now we can solve this with a real simple, quick chain rule. We've got the guts of the 3x plus 1 in there. So the derivative of the outside, pulling the negative 4 out front, gives us negative 8, 3x plus 1. Subtracting 1 from the exponent, negative 5. We just have to multiply by the derivative of the inside, which is 3. Simplifying then, 3 times 8 is negative 24. The negative exponent moves it to the bottom. We have 3x plus 1 to the positive 5th power. And much quicker and cleaner, we get to the correct answer. Sometimes it's worth it to take a moment and look at the problem at the beginning. What are the parts? Can we make it easier? How are the parts going to affect the way we calculate the derivative? Today's assignment takes a look at some of these chain rule problems where you recognize the guts, and then you take the derivative of the outside times the derivative of the guts. Take a really good look at it. Tomorrow, exponents and logs is going to be the lesson, and we use a lot of chain rule in those. So take a look at these. We will see you in class tomorrow.